This meeting is being recorded.
Okay. Good evening. Sharing the screen. Is it visible? Once respond. Is it visible?
Yes, sir.
Okay. So today we'll see, last class we have seen about the number system. No? Today we'll see about this representation of negative numbers. Okay? Representation of negative numbers. Representation of negative numbers. The negative numbers are represented in three forms. One is sign magnitude form. Sign magnitude form. Sign magnitude form. And second one is 1's complement form. 1's complemented form. And third one is 2's complemented. 2's complemented. So these are represented in three forms. One is sign magnitude form, 1's complemented form, and 2's complemented. Okay. So here each and everything we'll see in clearly. Suppose first sign magnitude form is there. Sign magnitude form. The sign magnitude form. So what you are doing, write the magnitude of a number. Okay, first write the magnitude. Magnitude of the number means what? You know that magnitude means what? Value of a number, no? So magnitude of the number in binary. Okay, write the magnitude of the number in binary. So first you need to write the value of the number in binary, and suppose if it is a negative number, you need to add 1 before this. Okay, if it is positive number, you need to add 0. Okay, so that means MSB bit will decide the given number is positive or negative. Okay, so if MSB bit is 0, the given number is positive, and if MSB bit is 1, the given number is negative. Okay, so given number is negative. Okay, so in this there are two different forms for zeros. For representing 0, there are two forms. There are two forms. Okay, two forms are there. This we will discuss. Okay, why for the representation of zeros there are two forms are there that you need to remember. Suppose like example, suppose +3 is there. Let us take +7. Okay, so +7 actually, so if it is in binary, so how it is represented? So 3 1's, no? So 3 1's is nothing but +7. So if you represent in 8 bits, okay, if it is represented in 8 bits, so 7 bits you write the value. So that means 7 bits. What are the 7 bits? 0 0 0 and 0. Okay. Okay, so we'll see. That is plus 7 if you take. So plus 7 is so 111. This is the value. So if it is represented in 8 bits, so this is 0, 0, 0, and next 0, 1, 1. Okay, 111. This 0, this MSB is 0 means what? Plus 7. MSB is 0 means what? It is a positive number. Okay. Similarly, same thing if I write minus 7. Okay. So minus 7 means actually it is represented the value. First you write the value. And if it is represented in 8 bits, so how it is representing, that is MSB will decide the given number is positive or negative. If it is 1, given number is negative. 0, 0, 0 and 0, 111. Okay. So 0, 111. Suppose minus 9 is there. So minus 9, how you are representing? Actually value is 1001. Okay. So 1001 means what? So 1001 is the value. And next 0, 0, 0. And this 1 is nothing but MSB is 1 is nothing but given number is negative. Okay. MSB decides the given number is positive or negative. If MSB is 0, the given number is positive, and MSB is 1, the given number is negative. Okay. So this is signed sign magnitude representation. Okay. And next is 1's complement representation. So second one is 1's complement representation. So 1's complement representation. So here what you need to do, suppose positive numbers are there. Positive numbers, those are represented in original form only. Okay, original binary only. Okay, original binary number only. Whereas negative numbers, we need to apply the 1's complement of positive number. Okay, so 1's complement of a positive number, you will get a negative number. Suppose example like how to apply 1's complement, I think you know. So that means simply changing zeros to 1, zeros to 1's, and 1's to zeros. Okay, 1's to zeros. Okay. Suppose like plus 7 is there. Okay, so plus 7. So how it is representing? So normally it will represent, that means 0, 111. Okay, so normally it will be represented in binary form. And suppose if you want to represent so minus 9 is there. Okay, minus 9. For plus 9 you know. Okay, so plus 9. So what is the value? Suppose if you consider, that means 1, 0, 0, 1. This is 4-bit, and you add one more 0. So for minus 9, just simply changing 1's to 0's and 0's to 1. So what you are getting? So this is 1, 0, 1, 0. Okay. So that means negative numbers are represented in 1's complemented form. Okay. So this is 1's complement representation. And next representation is 2's complement representation. Complement form. 2's complement form. So that means normally positive numbers are represented in original form. Okay, positive numbers are represented in original form. Okay, original binary form. Okay, or sign magnitude form, binary form. Okay, same as sign magnitude, but for negative. Okay, so negative, you need to apply 2's complement. Okay, how will you get 2's complement? You need to apply 1's complement, and adding 1 to this, you'll get the 2's complement. Okay, so so that means in 1's complement also you have for 0 you have 2 representations, but for 2's complementation, for 0 you have only one representation. Okay, one representation. Example, if you take, suppose plus 7 is there. So how to represent this one? This is 0, 111. Okay, 0, 111. minus 9 is there. Okay, so minus 9, how we are representing? That is actually plus 9 is how much? Plus 9 is 0, 1, 0, 0, 1. Okay, apply 1's complement. 1's complement. So that is 1, 0, 1, 1, 0. Adding 1 to this, you'll get the 2's complement. So this is 1, 0, 1, 1, 1, 1. Okay, so 1, 0, 1, 1. Okay, this is the representation for minus 9. Okay, so negative numbers are represented in 3 forms, that is sign magnitude form, 1's complemented form, and 2's complemented form. Sign magnitude form, so that means MSB decides the given number is positive or negative. So if MSB is 0, given number is positive, and if MSB is 1, given number is negative. So in the sign magnitude form also, for 0 there are 2 representations, and in the 1's complement, so positive numbers are represented normally in the binary form only, that is sign magnitude form, and negative numbers are represented in 1's complemented form. And for 0, you have 2 representations in 1's complement, and for 2's complement, so positive numbers are represented normally in binary form, but negative numbers are represented in 2's complementary form. But for 0, we have only 1 representation. Okay, this is about this one. And coming to the range. Okay, so what is the range? Range of the numbers. Okay, so range of if you take integers, range of the integers, sign magnitude form, sign magnitude form. The range is 2 power n minus 1 minus 1, and here up to so on minus 0 plus 0. Okay, up to so on you have this is minus. Okay, minus plus 2 power n minus 1 minus. Okay, this is sign magnitude. Okay, and next you have 1's complemented form. So 1's complemented form, if you see, the same thing is there, like minus 2 power n minus 1 minus 1, to so on minus 0 plus 0 up to so on plus 2 power n minus 1 minus 1. Okay, and third 2's complemented form, 2's complemented form, you have so minus 2 power n minus 1 and 0, you have only 0, to so on 2 power n minus 1 minus 1. Okay, these are the ranges. Suppose if you take n equal to 5. Okay, n equal to 5. So what is the range for sign magnitude form? That means 2 power 5 minus 1. So that means minus 16, minus 16, minus 15. Okay, so 2 power 4 is 16, and minus 1 is 15. So so on, and minus 0 plus 0 and plus 15. Okay, and next if you take 1's complement, same thing, minus 15 and minus 0 plus 0 and plus 15. Okay, and if it is 2's complemented form, you have minus 16 to so on plus 0. Okay, only 0 is there, and so this is plus 15. Okay, this is the range. Okay, this is the range of if you take the example n equal to 5. Okay, and next if you see, so I want to represent the numbers from plus 3 to minus 3 in 3 forms, that is sign magnitude form, 1's complemented form, and 2's complemented form. Okay, so that means number, and next sign magnitude form, 1's complemented form, 1's complemented form, and 2's complemented form. Okay, so if you take plus 3 is there, So plus 3, how we are representing in sign magnitude form? Suppose if it is in 3 bits, 0, 1, 1, and 0, 1, 1, and 0, 1. Okay. And if it is plus 2, how we are representing 0, 1, 0, 0, 1, 0, and 0, 1. Okay. And if it is plus 1, so 0, 0, 1, and 0, 0, 1, and 0, 0, 1. And if it is, let us take plus 0. Okay. So plus 0 you are representing as 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. And minus 0, how we are representing minus 0. So if it is a sign magnitude form, it is represented. MSB will decide the given number is negative or positive. If it is a negative number, so 1 and this is 0, 0. Okay. And 1's complemented form means for plus 0, you need to apply 1's complement. That is all 1's, changing zeros to 1's and 1's to zeros. And 2's complemented form, for 1's complement, if you add plus 1, what you are getting? 0, 0, 0. Here you are getting 1. So this you can neglect. So this is in 0, 0, 0. Okay. And minus 1, what is the representation? This is 1, 0, 1. Okay. And for plus 1, you need to apply 1's complement. What you are getting? 1, 1, 0. Okay. And adding 1 to this 1's complement, you are getting 1, 1, 1. Okay. And minus 2, so 1, 1, 0. Okay. So this is negative. MSB decides the given number is positive or negative. And next, 1's complement, plus 2. For plus 2, you need to apply 1's complement. This is 1, 0, 1. And adding 1 to this 1's complement, what you're getting? 1, 1, 0. And minus 3. So minus 3, this is 1, 1, 1. And 1's complemented form, for plus 3, you need to apply 1's complement. That is 0, 1, 1. Changing 1's to 0s and 0s to 1. So you're getting 1, 0, 0. And adding 1 to this, you are getting 1, 0, 1. Okay. So from this, can you identify any? So from starting onwards, I'm telling you, like for 0, there are 2 representations for sign magnitude form and 1's complemented form. And for 2's complemented form, here you have only 1 representation for plus 0 and minus 0. So that's why mostly in computers or in our Verilog language, so whatever the number you are giving, either it may be binary value or decimal value, octal or hexadecimal. So basically the compiler will convert that number into binary value. So if you are giving a negative number, so compiler will convert that negative number into 2's complemented form. Okay, it will not convert into 1's complemented form or 2's complemented form. Why? Because there are 2 representations are there. So compiler can't decide either which value for plus 0 and minus 0. But for 2's complemented form, you have only 1 representation. That's why the negative numbers are represented in either it may be in computer or it may be in Verilog language or any programming language like C, C++, like that. Negative numbers are represented in mainly Verilog as Verilog. This is represented in 2's complemented form. Okay. So that you need to remember. Okay. So this is about sign magnitude, 1's complement and 2's complement. Okay. And next we will see the subtraction by using r minus 1's complement and r's complement. Okay, r minus 1's complement and r's complement with the one example I will tell. Suppose if it is r minus 1's complement, if it is like binary, you have which complement? You have 1's complement subtraction. And if it is XS3 or BCD, you have 9's complement subtraction. If it is hexadecimal, you have 15th complement subtraction. 15th complement subtraction. Okay. And next, R's complements. If you take the R's complement, if it is binary, you have 2's complement subtraction. And here you have 10th complement subtraction. And here you have 16th complement subtraction. 16th complement subtraction. So that means R minus 1 complement I can call as which complement? R's complement. Okay. And R's complement I can consider as evens complement. Evens complement subtraction. Okay. So basically, I'm interested to do this. Okay. I will explain you about this 1's complement and 2's complement subtraction. So the process is same. You can do with you can practice with the XS3 and as well as hexadecimal subtraction. Okay. So 1's complement subtraction I will tell you first. 1's complement subtraction. 1's complement subtraction. So this we are going to use in the parallel subtractors. Okay. So mainly we'll do there with the 2's complement subtraction. We'll design the 4-bit 4 bits. We'll take minute and subtrahend at 4 bits, and we'll do the 2's complement subtraction. So there you need to know this how we are doing the subtraction. So let us take two values. Let us take 12. So 12 is in binary. What is the number? 1100 and 3. Okay. So 3 is nothing but 0011. Okay. So let us take this is nothing but minute and this is nothing but subtract. Okay. So normally internally what it will do, a minus b, it will do like this, a plus minus b. Okay. So that is a plus, negative numbers are represented in 3 forms. No. So this can be represented as a 1's complement or 2's complement. Okay. So this, so here I'm using negative number as 1's complement. Okay. So normally, so 12 minus 3 is how much? 9. No. So 12 minus 3 is 9. So first you need to apply the 1's complement for the subtrahend. Okay. So 1's complement for subtrahend if you apply, so 1 1 0 0. Okay. Adding to the minute. So what you are getting? 1 1 0 0. Okay. So if we are adding to the minute, what you are getting? 0 0. This is nothing but you are doing L minus S. That means larger minus smaller. Okay. So this is the larger value and this is the smaller value. And 1 minus 1 is 0 and 1 and 1. Okay. So you are getting a carry. 1 plus 1 plus 1 is how much? 1. 1 and carry with carry 1. Okay. So you need to add the carry to the LSB bit. Okay. End around carry. So end around carry. So if you are adding, what you are getting? 1 0 0 1. Okay. So this is nothing but what? 9. Okay. Plus 9. So is it verified? So if you are getting carry in the 1's complement, you need to add the carry to the LSB bit. Okay. So this is L minus L. Suppose if it is S minus L. S minus L. So what is S? This is nothing but minute. Okay. Minute is 3. 3 means what? 0 0 1 1. And next minute subtrahend. Okay. Subtrahend is a larger value. And this is 12. This is 1 1 0 0. Okay. First you need to apply the 1's complement for subtrahend. Okay. If you apply 1's complement for subtrahend, what you are getting? 0 0 1 1. Okay. 0 0 1 1. Add it to the minute. What you are getting? 0 0 1 1. Okay. So 0 plus 1 plus 1 is how much? 0 with carry 1. 1 plus 1 plus 1. So 1 with carry 1. And 1 plus 0 plus 0, this is 1. And here you are getting 0. Okay. So here no carry. Okay. So no carry means you can understand that given number is negative. So this is the intermediate result. Okay. This is not my actual result. Again, you apply 1's complement for the intermediate result. So what is the result? That is 1 0 0 1. So this is nothing but what? 9. You need to keep negative sign. So that means 3 minus 12. This is equal to what? Minus. Okay. So if it is S minus L, it is S minus L. So what you need to do? So you need to do the 1's complement for the subtract and add it to the minute, and you are not getting a carry. So you can understand that you are doing the smaller minus larger and you are getting negative value. So this is not my actual result. Again, you apply 1's complement. So that you apply the negative side. Okay. So this is about the S minus L. Okay. And next, suppose I'm doing same thing with 2's complement subtraction. 2's complement subtraction. 2's complement subtraction. If you take so first L minus S you will take L minus S. So that is minute. What is minute? That is larger value 12 and smaller value. This is subtrahend. Subtrahend is 3. Okay, 12 minus 3 is 9. So this is 1100 and 3 is 0011. Okay, first you apply the 2's complement for subtrahend. Okay, subtrahend. Subtrahend. First apply 1's complement. What you are getting? So this is my subtrahend. 1100. Adding 1 to this, you'll get 2's complement. 1101. Add it to the minute. What is my minute? 1101. You add, you are getting 0. 1 plus 1 is 0. Add it to the minute. This is 0. So 12 is 0. So 1 plus 0 is how much? 1. 1. And this is 0. 1 plus 1 is 0. And 1. 1 plus 1 plus 1 is 1. You are getting a carry. So discard the carry. Here you need to discard the carry. In 1's complement, we added the carry to the LSB. No? Here you need to discard the carry. So my value is how much? 1001. Okay, this is nothing but plus 9. Okay, plus 9. I got plus 9. This is L minus S. Okay, L minus S. And next S minus L we'll see. S minus L. So S minus L, how we can do? So that means minute is S. So S is how much? 3. So 3 is 0011. And subtrahend. Okay, so this is subtrahend. Subtrahend is larger value, that is 12. 12 is 1100. First you need to apply the 2's complement for subtrahend. Okay, for subtrahend. So if you apply first 1's complement, changing zeros to 1s and 1s to zeros, 0011, adding 1 to this, 0, 0, 1 plus 1 is 0, carry 1. Again, 1 plus 1 is 0, carry 1 and 0. Okay, so changing, so this is 1's complement and I am adding 1 to this. Okay, and add it to the minute. So this is 0011. So if you add, what you are getting? 1110. Okay, so no carry. If it is no carry, understand that you are doing S minus L, the value is negative, and this is the intermediate result. This is not my actual result. Again, you need to apply the 2's complement. Again, you need to apply the 2's complement. So that means 1000, adding 1 to this. So what we are getting? 1001. Okay, this is nothing but minus 9. Okay, so minus 9. Okay, so like this, you can do this subtraction. Okay, subtraction using 2's complement and 1's complement and 2's complement. Okay, and next I want to say about this binary codes. Okay, binary codes. What are the binary codes? Binary codes. So you need to know about these binary codes. first is weighted codes. Okay, weighted codes. What are weighted codes? Weighted codes are nothing but each digit position has a weight. Okay, each digit position has a weight. Suppose you have binary and BCD. Okay, so binary have what weight? 8421. Okay, so binary have 8421. We already seen like converting any other number system into decimal. So we added with summation of digit into 2 power or r power place value. Those are nothing but weights. Okay, so like summation of digit into r power place value. This is nothing but what? Weights. Okay, so that means 8421 or 2421. Okay, 2421, 3321, 3321, 4221. These are nothing but weighted codes. Okay, and BCD also. The range of the BCD is what? From 0 to 9. Okay, weighted codes. And next is non-weighted codes. Non-weighted codes. So non-weighted codes means what? There is no any positional weight for this non-weighted codes. Okay, like XS3 code, gray code, gray code. So gray code means what? In the K-map, we are following gray code sequence, no? 0, 0, 0, 1, 1, 1, and 1, 0. Okay, there is no weight, so we can't say there is value for the gray code. Okay, there is no weight for gray code. Okay, for XS3 also. And this is non-weighted codes. And next you have reflective codes. Reflective codes. So reflective codes means what? That is first n by 2 values compared with those of last n by 2 values are reverse order. That means complemented with each other. So let us take 2421 and 5211 and XS3 code. Okay, so XS3 code. So I'll take the example of XS3 code. Suppose what is XS3 code? Suppose if it is binary and XS3 code. So that means 0, 0, 0. What is XS3 code? 0, 0, 1, 1. Okay. Let us take this is BCD. Okay. The range is 0 to 9 only. 0, 0, 0, 1. This is nothing but adding 3. You are getting adding 3 to BCD. You are getting XS3 code. This is 0, 0, 1, 0. This is 0, 1, 0, 1 and 0, 0, 1, 1. This is 0, 1, 1, 0. 0, 1, 0, 0. You are getting what? 0, 1, and 0, 1, 0, 1. You are getting 1, 0, 0, 0. Okay, and 0, 1, 1, 0. What you are getting? So 1, 0, 0, 1. Okay, and next 0, 1, 1, 1. You are getting 1, 0, 1, 0. So 1, 0, 0, 0. You are getting 1, 0, 1, 1. And 1, 0, 0, 1. What you are getting? 1, 1, 0, 0. Okay. So that means if you apply 1's complement for this one, you are getting this value. Okay. So that means 9's complement of first number is the, so that means first number, if you apply 9's complement, you are getting the last number. Okay. So that means if you apply 1's complement for first number, you are getting the last number. Okay. And suppose if you apply 1's complement for this one, this number, you are getting the this number. Okay. Second number, this number you are getting. If you apply 1's complement for this one, you are getting this one. Okay. And similarly, if you apply 1's complement for this one, you are getting this one. So if you are applying 1's complement for this one, you are getting this one. So this is nothing but reflective codes. Okay. So if you apply 1's complement for first number, you are getting the last number. Okay. That's why we call as reflective codes. Okay. So that is nothing but reflective codes. And next is sequential codes. Sequential codes. Sequential codes. So what are sequential codes? Like each succeeding code is one binary number greater than the preceding. Okay, so each succeeding code is one binary greater than the succeeding. Suppose the 8421 and XS3 code or sequential code. Suppose you take a binary number, so that means 000 and 0001. Okay, if you compare these two, this each number and the succeeding code is differ by 1 bit. Okay, that means it is greater than, no, it is 0 and it is 1. Okay, so greater by the preceding. So if you compare this one and this one, so this is greater than this one. Okay, that's why we call as sequential codes. Okay, and next is the alphanumeric codes. Alphanumeric codes. So alphanumeric codes are nothing but ASCII codes. ASCII codes. ASCII codes, like in the computer, so many small characters and large characters, special symbols, and shift control, all these are there, no? So that means ASCII is actually American Standard Code for information interchange. This is of 7 bits. Okay. So internally, each and every character or any special symbol has specific ASCII code. So if you are pressing any key, so computer can understand that that is suppose if you are pressing A, so that is having a fixed ASCII value. So that is given to that is going into the processor. So computer can understand that A is pressed. Okay, based on that, it will process. Okay, this is standard codes ASCII. Okay, and if you want, that means next is next is ABCD code. ABCD code. This is nothing but extended binary coded decimal. Okay, so this is one of the extended code. Okay, you can remember. So that the codes which consist of what numbers, alphabets, and characters are nothing but alphanumeric codes. Okay, and last one is error correcting, and detecting codes. Error correcting and detecting codes. So error correcting, detecting codes are nothing but mainly this is used with we need to add the extra bits in the detection and correction. So we'll use in the communication like Hamming code. Okay, so we already came across Hamming code, and parity code. Okay, so these are the codes you have. Okay, so this is about today's topic. Today we discussed about the representation of negative numbers. Those are represented in 3 forms. One is sign magnitude form, 1's complemented form, and 2's complemented form. And we have seen how to do the subtraction by using 1's complement and 2's complement. In that we have seen larger minus smaller, smaller minus larger. Basically we have seen the 1's complement and 2's complement subtraction. And next we have seen the this codes. Okay, what are the codes? You have weighted codes, non-weighted codes, reflective codes. Okay, so you need to remember that the XS3 code comes under the non-weighted code and reflective code. Okay, and sequential code also. So one of the means that they can ask in the bits like XS3 code comes in which codes. Okay, so this is one of the important like it will comes in the non-weighted code, reflective code, as well as sequential code. Okay, and also we are seen alphanumeric codes and error detection and correction codes. Okay,